Okay, the biggest way that we are going to measure concentration is called molarity. And that is really, really common. So we're going to focus a little bit more on this. So by definition, molarity is moles of the solute, the thing that's being dissolved, divided by liters of solution. And again, that's both the solute and the solvent. So when you're doing a problem, make sure you identify the solute and then identify the liters of solution, not just the solvent, but the solution, and then divide them, and that's molarity. So for example here, we have 5 moles of sugar dissolved in enough water to make 1 liter of solution. And notice the terminology. I'm saying dissolved in enough water to make 1 liter of solution. I'm not saying dissolved in 1 liter of water. Now granted, it'll be about the same, but it's technically the solution. So realize then if I do that, it's 5 moles divided by 1 liter, 5 molar solution of sugar solution. Okay, so let's just do a couple of problems here. If I want to calculate the molarity of a solution prepared by dissolving 11.5 grams of solid NaOH, what I'm going to need to do is convert this to moles. Okay, so you're going to want to take a second to dig up your periodic table and find out what does 1 mole of sodium hydroxide weigh. So sodium is 23, oxygen is 16, and hydrogen is 1. And so we have 40 grams for 1 mole. All right, and so then what we're going to do is take that 11.5 divided by 40. We're going to get 0.288 8 moles. It doesn't really matter. Sig figs at this point, they don't really matter. Now, I'm going to take that many moles, I'm going to put it in enough water to make 1.5 liters of solution. So on the bottom, I just go ahead and divide that, and I get 0.19 molar solution. Now, I could call this a big M, because that means the big M means molarity. I could leave it as little m, or MOL, moles per liter. I could do that. I could do the big M. You'll see it both ways. All right, so again, if we have 1.56 grams of hydrochloric, well, it's not an acid until you dissolve it, but hydrogen chloride, I'm going to again convert that to moles, and chlorine is 35.45, hydrogen is 1. So a mole of HCl is 36.45. And so all I'm going to do here is take 1.56, divide by 36.45, and I'll get moles, 0.0428 moles of HCl. Now, I'm going to divide that by the liters of solution. So notice we have milliliters, so I'm going to divide that by 0.0268 liters. Divide it by 1,000. 1,000 milliliters are in a liter. And so then what we're going to do is take that, divide by 0.02, whoopsie, 68, and we'll get an answer of 1.60 molar. Okay, and again, that can be moles per liter, or just the big M means molarity. All right. Now, the other way that can happen is you are given the molarity. If you are given the molarity, it says how many grams of something can be used to make a liter of it, 0.2 molar. It's very common if you ever are a TA in a chemistry lab or something like that. They will ask you, hey, I need you to make up a solution. And you know that you're supposed to make up a 0.200 molar solution. Now I'm going to go ahead and write that big M as moles per liter because that's what it really is. And then, again, you know I'm not much one for ratios, more dimensional analysis. So if I multiply the volume times the molarity, what happens is the liters cancel and you are left, in this case, with the same number because it's just 1, but you're left with moles, not molarity. So when you take your volume times your molarity, liters will cancel and you'll left with moles. But just make sure it's liters, not milliliters. But once you have liters, multiply, you'll get that. And then at that point, all you have to do is convert back to whatever that moles. Okay, so take a second here and find out what that weighs. We have K, which is 39. We have chromium, which is okay, so if we do 2 potassiums each at 39, 2 chromiums each at 52, and 7 oxygens each at 16, we get 294. And so when we multiply that by 0.2, we get 58.8 grams. So it's important that you realize that this is going to be weighed out. This is a really pretty orange crystalline, very toxic, but very pretty. And what's going to happen is you're going to weigh out 58.8 grams of this stuff. You're going to put it in an Erlenmeyer flask or a volumetric flask. You're going to add water up to the liter point. You're going to stir, and when it's completely dissolved, you will have a 0.2 molar solution of it. You'll have a liter of it. All right, another thing that we have to talk about here is the fact that we can break these things up. And when we break these things up, it's important to realize that they're going to break up into parts. And so let's just take a second to visualize what's going on here. We've got the potassium ion with a +1 charge. You know it's a +1. Well, there are 2 of them, and the reason that there are 2 of them is because this polyatomic ion dichromate, okay, you might recognize that a little bit, the dichromate polyatomic. This works as a unit. Remember, that's a covalently bonded thing but has a charge, so now we're talking about ionics here. What happens here is if we were to break this up, dissolve it in water, we have 2 potassiums and we have 1 dichromate. And so when we look at our molarity, we had a molarity of 0.2 molar of the whole thing, right? 0.2 molar of the whole thing. So if I have a 0.2 molar solution, but what's going to happen now is I'm going to break it up. I'm going to get double the potassiums. Now, I'll still have just the 1 dichromate. Here's the 1 dichromate. Here are the 2 potassiums. And so, you know, that's why we spent so much time in Chapter 4 just talking about the naming and the fact that this is considered a unit of dichromate. And it has a -2 charge. And then there are 2 potassiums, each with a +1. So what this is going to mean is the concentration of potassium, and by the way, we often show concentrations with brackets. You don't have to, but that's how it's often done, is 0.2 molar times 2 is 0.4 molar. The dichromate, there is only 1 dichromate, so it's 0.2 molar times just the 1 that's there. There's only 1 dichromate in there, so it is 0.2 molar. That's if you break this up. It's just like we've talked about this idea before. You have 1 person, and we talked about like the concentration of people in the room is maybe 20 people in the room, although we can't do that anymore, social distancing. But if we were able to get 20 people in the room, then we talk about, well, the concentration of people is 20 people. But what if we wanted to talk about the concentration of arms? Well, then we would have double that. We'd have 40 arms per room. So it's really just what are you looking at there? Okay. All right, so you should take a second to do the check for understanding here. So pause the video and do that just to make sure, and then just start it up again. And the molarity is 4.5 grams of sugar. 1 mole is 156 grams. And so we're going to get 4.5 divided by 156. So 0.0288 moles. And then we're going to divide that into enough water to make 200 mils of solution, or 0.200 liters. So just make sure that you divide by 1,000 to get liters, and then we're going to have 0.144 molar. Okay. Again, here when you start out with a molarity, go 0.2 moles per liter, multiply by liters. Okay, so get that mils into liters. Okay, they're going to cancel, and you're going to get left with moles, and this is going to be copper chloride. Then just look up on the table, what does copper chloride weigh? And chloride is going to be 35.45 each, and there are 2 of them. Plus we have 63.55 with the copper, so 134.55. Now, if you round that, it's okay, because the answers on the test will not be that close. You'll be able to tell which one would be the right answer. We're kind of reduced to doing multiple choice. And again, what is the concentration of molarity for the copper ion and the chloride ion above? So again, just make sure that you've got this idea here. They're going to break up like that, 2 chlorides and a copper. So the copper concentration will just be the same. There's just 1 of those to every 1 of the copper chlorides. The chlorides, there are 2 of them, and so this will be 0.4 molar.